welcome to this very last presentation time slot on this topic of friction stir welding, FSW, and processing, FSP. Those are the two topics that we have been involved in at AB for the last couple of years. So a special acknowledgement to Dr. Ali Amouri, who's been our graduate since June 2003 in the PhD program. He's one of 3 graduates. Ms. Zaina Al-Shlu, she's a PhD student currently. And may his soul rest in peace, Mr. Ali Khairuddin, who's our ME graduate in 2013, who passed away a few months after graduation on his job in South Africa due to an accident. He'll be missed. All right, well, this work, again, spans several years, and we have 2 projects that funds this work. One is a URB project, the other one is a QNRF project. It's a 3-year project that will actually end at the end of this year. And they both have, I highlighted this basically in red, they both actually highlight friction stir welding or processing. So if you see the word FSW or FSP, you know what I'm talking about. We have done a lot of publications on these 2 topics. These are basically journal publications. We have also done a lot of the conferences as well. You see ASME and Variety. It's been very extensive publication record on this one topic. Before I start, I'd like to just go over with you quickly on the overview of the presentation. First, I'll speak about the introduction. Second, about the FSW, friction stir welding and processing, the setup that we have developed at AB the last couple of years. A case study of characterizing of magnesium friction stir welded joints. The fourth topic is modeling for finite elements modeling purposes. Which material model do you select? And then I'll speak about bimetallic joining of magnesium to aluminum, again, FSW. Then we'll do one more case study of laser-assisted FSW of basically 1045 steel, medium carbon. And then we'll go about quickly about some of the planned work in the future in the FSP, FSW area. Before I go, let me just speak quickly about the history of FSW. If you see FSW or FSP, they really mean one thing, which is basically it's a solid state joining technique. And let me just give you a quick idea of what that means. If you look at welding that have to do with fusion operations, they actually melt the material, base material. If you look at this specimen I brought here from Germany, which is basically a copper specimen, this is a welded by FSW process. And so this will never melt. If you look at the solid weld, you appreciate the quality of the weld. They also take to it another piece which actually broke away from the weld. So this weld was a solid state weld. It was still good enough that the breakage actually happened away from the weld. So the strength of the material at the weld is stronger than that in the weld material. And the question is why? I'll come back to this again during the presentation. This invention was done in 1991 by the Welding Institute back in 1991 by these 3 gentlemen who happen to be British. This process is sustainable, so there are no consumables, no pre and post steps needed, and low energy and temperatures involved. Again, it's a solid state process. Quickly again, examples of friction stir welded joints, joining of axles onto differential housings, aircraft paneling. Anytime you say aircraft, that means usually aluminum. This is the most common these days. Rocket fuel tank, as well as joining of 5-meter diameter tubes. So when you talk about this thing, basically those are the tubes that will cool atomic power plants, perhaps some of the gas and oil industry that's about to hit this country hopefully soon. So how does this work? If you look at the basics of this thing, you see a pinned tool with a big shoulder. So this shoulder basically, as that spindle spins and rotates, the tool is actually being fed almost similar to machining. So a lot of spinach and slow feed, tool feed. What happens is the rubbing of the shoulder against a workpiece metal will create friction and thus heat, while there is a lot of thrust force from the top down, which keeps the pressure in contact. what this little pin right here is actually the stirring portion of the friction stir welding. So there's a friction from the shoulder and stirring from the pin. If you combine the action of heat generation as well as the stirring mechanism, you get a lot of hot deformation at really high, very high strains and strain rates. And in fact, if you look at this before and after, before there's a seam between those, this is a butted joint basically. So there's basically this is the opening, and right behind it, voila, there's a weld. Again, solid state weld, and this is what makes it so interesting. Let's see if I could make this video work. So this thing's constituted by basically 4 phases. One is a plunging phase where the tool actually plunges down. The dwelling, it sits here for a little while while it collects heat, and then the tool traverses at a feed, again, relatively slow. Now it retracts, leaving behind what we call, this is a very characteristic or telltale sign of the FSW process, that little, basically just a little hole that is left behind for some reason. There. So basically there is that exit hole right there. There's ways to fix that, but I will not speak about that right now. All right, so enough about the introduction. Basically what happens if you compare this to a liquid-based, fusion-based welding, you see some characteristics that are similar and some that are different. For example, the nugget or the stir zone, there is one in solid-state friction stir welding. There is one in fusion-based welding. There is a HAZ, which is heat-affected zone, in solid-state welding, while there is one in FSW welding. Now, this is relatively new, this topic, thermomechanical affected zone, which is a TMAZ, which is, again, it has some mechanical deformation and some heat as well. There is the welding direction, and there is the advancing side, and there is a retreating side. This is very, very important when it comes to, especially welding of different metals and bimetallics. You really have to know exactly which is the harder. For example, aluminum and magnesium, which we do, you have to offset the tool in the advancing side direction so that you actually create more motion. So first, let me just talk about the actual setup at AUB. We spent about 2 or 3 years developing this whole thing. This is a CAD model of the fixture, relatively simple fixture basically. This is the workpiece, and this is the, it has to be a very rigid fixture. There's no question about that because it has to take a lot of thrust force, as we said before. And if you do this correctly, then this is the setup, and this is very typical resulting joint. The tool is the most important thing that you probably think about. The tip is very, very different from application to application. In this case, basically, it's a concave tool. It has to be made from tool steel, which has to take a lot of heat, a lot of wear. And this is very typical, in our case, again, in bimetal welding. This is the setup that we have on the Haas machine, modified. So if you look closer, you will see, basically, this is the setup that we have. We have invested a lot of money in this machine, but it has been a wonderful thing for us over the last 10, 12 years. This is set up. Basically, we have a lot of force. We have 2 Kistler dynamometers. One is rotating, one is fixed. We have temperature monitoring. We have thermocouple sensors. We also have infrared sensors as well, which have been a wonderful thing that they're all instrumentized. We have a lot of good data from that setup. Let me see if I can just play this video for you. It's a quick video that illustrates the process as well. Is it obvious? Is it clear or no? Yes. Yeah? So we dim the lights, please. إذا في مزيان من عندي خلفنا نرى لهيدي. Light on, light off.
Okay.
Light on. خلاص هيك منيح. خلفنا نرى. Anyway, so there's a video that shows basically how it works, and it's almost like a machining. It's like milling, almost like milling, except the tool does not cut. And there. Again, the tool is spinning, and it's being fed in this direction. And this is all it takes. If you have the parameters correct, it looks very simple, but it's also very complicated. But if you know what you're doing, you have made, in fact, a solid-state weld. So this is FSW. Basically, weld, in this case, shown is a butt weld. So what is FSP? FSP, it looks like this. Basically, a solid plate that looks just like this magnesium plate, which happens to be a very light magnesium. So if you take this piece of magnesium and you do FSP to it, with no welding, what do you expect to get? This is what we call friction stir processing. And the answer is that very obvious. You take that tool and you run it across that plate. Anybody could guess about what would happen to that? And why do we do this?
Hardening.
Hardening, exactly. Very good. Plus one, yeah. So basically it's for grain control. If you know what you're doing. Remember that this weld resulted in stronger material in the weld in a way because we have refined the grains in the weld area. So we take advantage of that fact and we do FSP.
Please can you?
Keep up here. Off is off. Light off.
Yes. Okay. Thank you.
Yeah. So this basically is what happens when you do FSP alone. Look at we have a close-up of the weld area. And you're showing basically the weld cross-section superimposed on which is that tool profile. There is your shoulder, and there is that pin, and that thing is spinning again, and it's moving in this direction, away from the wall. And look, this is your nugget, the stir zone. This is the thermomechanical affected zone. This is the heat affected zone. Again, this is in very, very fine scale. So let's see if we have done the grain refinement as we said. We zoom in, one from the stir zone, another photo from the base metal. And as you zoom in, it becomes very obvious what we have done from the FSP. All right, so the histogram on the left, this is your base metal. Great distribution of the grain size, average 13 microns, look, maximum 20, versus the refined grain of the smallest about 6, I'm sorry, average about 6, smallest about 1.4. So this roughly is, the grain diameter is roughly half what you start out with. So it's a fantastic method to do fine refinement, and again, it's cheap if you know what you're doing. All right, this is a case of characterizing magnesium, AZ31B, which is one of the most common ones, being aluminum about 2.5 to 3.5% with some zinc. So this is also known as aluminum zinc, zinc magnesium, or magnesium aluminum zinc, for that one reason. And for that one reason, we're interested in this thing. This is, the Chinese just love AZ31B. They'd like to replace almost all the aluminums in their chassis, the structural parts, the die-cast parts, the engine, blocks, what have you, with magnesium. But again, it's a dangerous thing because magnesium has many, many it has some downsides as well. But if you look at the ASME's plot, as far as pure density and strength point of view, if you look at the metals portion of the ASME plot, ASME is not, I mean, he just made $1 million, or probably million, maybe British pounds, selling these kind of maps, which T plus strengths or modulus or what have you, versus density. So if you look at this plot, you see the density of all the metals, and magnesium is right there, about 1.7 density. The second closest one is aluminum, is about 2.7. So magnesium about maybe a third, 40% lighter than aluminum. So it makes a lot of sense for those sustainability people that would like to reduce the weight of the vehicle, make it more fuel efficient, improve the mile per gallon thing. Makes a lot of sense for the Chinese to go in that direction, but again, it has a lot of issues with corrosion. It's also not very stable thermally. In fact, you know, the Chinese made fireworks from magnesium. So if this vehicle ever catches fire, most likely not only the fuel will burn, but the car itself, the chassis will be on fire. So they'll go take that one. But I say, you know, there's a huge investment right now in magnesium. In fact, you'll be seeing magnesium in many, many applications, compared with steel, which used to be the thing in materials, which is about 7.8. So magnesium is about 6 times lighter. So that plate that you have is about 6 times lighter than steel, which is fantastic. All right, so let's go back to this. So again, we take magnesium to magnesium, and then we do FSW. You take that plate right there. We keep track of the advancing side, which in this case does not matter because they're both the same material. Retreating side, we make dog bone specimens out of those, and then we do a lot of the mechanical testing. So we keep track of which is failing where, basically. We have to know if it fails in the middle or away from the middle, and if it's away in retreating or advancing. We made a lot of experimental work. Was fully populated, actually. This matrix was huge, and again, you look at a jig right there. This is the broken sample. You do a lot of speeds, feeds, and the resulting strengths. We almost approached 100%, which is, in our case, is unbelievable. Most of the work that we have seen magnesium about is about 80%, so we have done better than what most people report up there. Now? Well, this is it. This is the good question, Daniel. So this is your base metal, which is right there, that solid. all right, which is your ductile. This is very typical for incubation until the jig basically just seats. But if you look at this is a typical magnesium. This is 94%, I believe. Look, solid, fine grain, no defects. So what we're suspecting is that the defects are actually killing the strength, not anything else. All right, so this in fact may in fact have finer grains than this one, but it has some defects, so it killed it prematurely. All right, but would love to again do 100% or even more than 100%. We spent a lot of time again characterizing the the samples to understand what has caused a failure. So again, red on the now again red. This does not mean that these process parameters are wrong. Maybe it just means that the defects are just the killer. And if you have done your homework, then you could actually design. This map is very, very significant. I think once we publish this is relatively recent. Once we publish this, it will be well received. If you let this tool just sit right there with increasing RPM at very, very low feeds, it will actually burn itself out. It becomes almost like fusion welding. You're actually melting. If you allow the feed to go really wild while the speed is low, you actually have cold welds. So either the cold welds or the, we call those melting welds, they're bad. So again, we avoid these red areas. This is the functional operational area. These are the feasible welds. But notice again, we plotted R equals 10 to R equals 2. So this is not diagonal, this is not 1 to 1. This is actually, probably start about maybe about R equals 5. So for low speeds, low feeds, R is about 5. For high speeds and high feeds, about R equals 1. So it's not diagonal. But those are recommended processing parameters. We examined more the grain structure. We plotted again histogram for the grain structure. We found out we received this is what we call actually this is called TRC magnesium. So this is actually this is roll cast. We call it twin roll casting. So really it's a molten metal that goes to solid very, very quickly, one process. So this twin roll cast magnesium is received by us at about 11.7 plus 6. So there's a lot of scatter in data, as you can tell by this histogram. We examined for one set of specimens the resulting grain structure, and look, there's some growth. There's some growth. So in the nugget, you see 13. So you have gained, the grain has grown. And the has, it's now 18, 16. So actually, there's definitely some growth. And we have done a lot of characterization on this thing. We were able, in fact, to come up with a very simple empirical equation that relates the grain size to your operating parameters. So in fact, an engineer does not really know anything about temperature or strain rates or strain. They know that, we put in speed and feed, we get grain size. So again, this has just been published, and we're able to, in fact, predict 14.3 compared to, for example, about 13 in the nugget. So again, we think this is a very good prediction. All right, so one of the most important things in modeling, now again, we don't like to do modeling alone or experimental, we like to do both. So if you like to do some simulations, you like to pick which material model or which considered law would actually suit best this processing, because again, we'd like to do some FEM simulations of the FSP and FSW. We're doing this for magnesium, we're doing it for magnesium to aluminum, we're doing this for steel, we're doing a lot of different materials. But we started out basically with magnesium. So you build your model, you do your fine mesh, basically the tool is, and you see the research question that we're facing is, can we find or identify a mechanical behavior, stress-strain equation, that will best model the behavior? The state variables that we want is relative temperature, strains, and strain rates. Temperature ranges all the way up to almost melt. Again, you don't want to melt. Once you melt this thing, this is no longer FSW or FSP. Strains are about 125% strains, extremely high strains. Strain rates vary from a low estimate of about 10 to about 1,000. Okay, we're measuring and we're estimating about 100, but those are the reported values. We examined many, many variations of these basic material models. So as the integral, basically, this does not allow for saturation, so it does not really actually have strain rate in it. While the Johnson-Cook has 3 terms, one for the strain, one for strain rate, and one for temperature. There's this Israeli-Armstrong model, which is relatively nice for us because it allows for HCP estimates. HCP is exact and close back, which is a lot more difficult to process than FCC or BCC. This is the reason why titanium, for example, is difficult to machine or to cast or what have you. So again, we'd like to look at the Israeli-Armstrong's modeling and see how close will help us with modeling. Before we go into really high strain and high strain rate regimes, we'd like to say if those models actually allow us to predict something very simple, just like see how a dog bone tensile machine will actually be modeled in FEM with those models. Is it a good model or is it a bad model? So take a look at your through stress, through strain for the dog bone specimen, and you look for how these models will compare. All right, so again, those are reported models. We also have a set of values that we also found from our own testing. But if you take a look at how the Johnson & Cook matches the experiments and how the, again, no saturation strain rate, strain is modeled by the Sellers-Taggart. So again, this is a straight line horizontal. Versus the Rayleigh, you'll find that, for example, Sellers-Taggart will overestimate stress at low strains and underestimate stress at high strains. While the Rayleigh-Armstrong we found to be a good fit for what we want to do. Again, at this point, only for the dog bone tensile specimen. We'll see how it fits. In fact, it fits throughout the entire range for many, many strain rates and temperatures. Once we're happy with this, let me just show you basically what the run would be like if it runs. So this is a typical deform run. Again, this is the tool, top view, side view, and it's moving in that direction. And it's giving you basically, in this case, how the temperature was, in fact, how the temperature is going. It's going up to, what was the final value? 600. 6. What's the melt? What's the melt for magnesium? It melts at 660. So again, this will allow us, now again, if you look at this area, right underneath the shoulder really, it's really close. So I see 600. 600. Yeah.
Why is the tool pitched?
The tool is not
Pitched.
You know, if you don't appreciate the complexity of the process, it's very simple. There's about 20 different input variables. One of them is pitch angle. 3 degrees is known to be a good inclination angle. And again, many of those things have been vetted out over the years. For example, this is a very important factor. The other one is the offset in the direction of the advancing, another big factor. In fact, we make
Pitching is really important. An important variable is
yes, it is. Again, look for example at the offset. If the offset is 1.5 mm in the direction of the advancing, then you get lousy welds. Make it 2 mm, you get very good welds. Okay, so again, it's that sensitive. Look at another run, and in this case, well, this has to do with we have to backtrack. There's something called Zimmer-Haldane. Zimmer-Haldane's Z parameter, which in fact is the maximum temperature and strain rate that the material or any point in the material has witnessed in the process, so that when we talk about dynamic visualization, which in fact is the reason why we have great refinement, we will know the history. And this is exactly what it is. In fact, if you look at it, those 9 points are tracked throughout this process, so that they all end up lined up in this. So basically, where they came from is what we have to know. The history and location, as well as most importantly the strain rate and their temperature history. Once we do this, then we can calculate what's known as a Z parameter. And anyway, we could get some things like strain rates and strains, compare those models. Temperature and stress, you see the stress variation is quite a bit different for all these 3 models. But again, from this we were able to, okay, look at this for example. We were able to compare our FEM with the experiments. We have the Kistler running, and we also have the FEM, and the fits are excellent. Of course, it was not as easy as it looks, but again, this is your FEM simulations. This is the experiment for thrust, for torque. So mechanically, we're solid. Once we have been able to verify this, we were able to really make really good contours of those important strain variables, the temperature, the strain rates, and those strains. And the Z parameter, which again will lead, Z parameter basically is a temperature modified strain rate, or strain rate modified temperature. If you know this Z, then the Z is related to the average grain size. So this really is what we're after. Now we have a map that actually tells us where the grain size or the grain size vary versus feed and speed. Again, for an engineer who does not know science or does not know Z parameter, this is very, very important. What am I doing on time, Cameron? Should I stop? Yalla, okay, خلاص make it quick. Okay, there's a lot of correlations. We know that we have good correlation between FEM and those simple equations that we have. Again, very simple equations that will be very valuable. And again, we have publications on this, so we'll receive. Another case is to bimetallic. Now, bimetallic, if you ask the Chinese what would they like to do, they like to use magnesium, but there's a lot of aluminum is left. So if you look in the structure of that car, for example, the chassis still has aluminum, it still has magnesium. So what happens when you marry the aluminum to magnesium? You have to do joints that are, we call this bimetallic. Many, many problems. In fact, right now, it's almost like a black art. One of the main reasons right now is there's an HCP on the magnesium side, there's an FCC on the aluminum side. How do you make this work? So we picked some aluminums. For example, this is almost pure aluminum. 661 is very, very common in structural parts, so it makes sense. And we married this to, again, you see the aluminum, it's a main component in the AZ31B alloy. And you take the samples from this thing, and you look for intermetallics. You look for intermetallics by, you take slices of this thing, you take the SEM, you do a lot of analysis, you take the XRD, this is the sample right there, and you do XRD measurements, you back out the bimetallics, and you look for the alphas and the alphas and betas and gammas structures, aluminum 12, magnesium 17. You look for, I'll try to speed up here actually. So you look at distribution of, what's happening. Is the magnesium going into aluminum or not? And those actual measurements from the, actually this was from EDX, the energy dispersive X-ray electron spectrum. And actually the analysis of this shows that there's a lot of mixing from the aluminum to the magnesium and so on and so forth. In fact, some are done at the surface, like that one, and some were done in the bulk. So this, for example, this came from this sample, and I can't see it quite right, but some of this, in fact, came from the actual cross-section of this thing. So there's some mixing. Again, we did this for the 661 as well as the 1100. We also did some Vickers hardness to see if there's mixing, and if there's intermetallics, intermetallics are extremely hard, and they will cause, in fact, a hardness noticeable change, and there it is. Okay, there's a big chunk. That means low hardness. Small imprint or indent, which is very characteristic of a hard impact. We'll go to the FEM. There is a lot of work there. Magnesium on one side, aluminum on the other side. Predictions of mixing of aluminum and magnesium, and so on and so forth. We tried to correlate this with the, this work is relatively new, so we have not published this. So again, FEM relatively agrees, again, at least qualitatively, with the FM results. So these are good results, we think. Big SIG being a big issue, we're trying to see, we put a steel shot, for example, on one side, and watch that thing in real life, as well as FEM, how the steel shot, in fact, moves around. This tells you if there's good mixing or good movement or no. FEM of temperatures. Laser-assisted FSW, we look at this for enhancement, especially in steels, you really need the extra heat. So look, in fact, at the phase change and volume fraction for the pearlite and martensite, how it changes with time, for example, at different speeds, for example. In this case, with time for this case, so as the pin passes right by the thing, you have a certain profile of temperature, and as it cools down, you see the pearlite and the austenite and the martensite, how they're forming for different temperatures. So again, this is very, very nice. At least, basically that you end up with, where the shoulder just passed, you have almost all martensite, which probably makes sense. All right, so where we go from here, we have planned some extra work. One is to involve some cryogenic cooling, and the other is to do some real-time FSP, FSW control, which will be very variable. It'll be difficult, but we'll try to do this in cryogenic. Right now, there's an FYP progress right now, work in progress. My students to actually have a controlled valve that will allow you to give or dial in basically a certain flow that you want, and then we'll allow them to do some experiments on the cryogenic stream. And what we really want to do is to freeze the grain growth. That's what we want, to actually prevent the grains from growing to 13, 15, 20 microns that we just saw before. There is work, as I said, on control. This was supposed to be Ali Amouri's main thing, but he did not, well. So we'd like to have somebody pick that up from Ali. And this is the flow chart that would like, basically, you'd like to, have prescribed grain. Say, I'd like to have, for example, 6 microns grain resulting. All these softwares that you have developed using the empirical equation that you have, and with the control thing, hopefully try to give that person the dialed in grain size that's respected. And I'm done. Thank you for listening.
Questions?
stresses in the same material, and also it's worse when you have two materials, and it's even worse when you start cooling it and freezing these grains.
Heat is better than fusion welding. In fusion welding, you're melting and the density is very high.
Right.
In this case, it's easier, it's all steam. But again, we really have not addressed this. There's a lot of issues. This is very, very important, especially for crack propagation and so on. The other issue is texture, because magnesium, unlike FCC, HB, is very difficult. And because twinning is a major thing, it may give you a rough surface. So texture is an issue that it is residual stresses. So we have not done this work, but I know it's very, very important. But definitely, again, compared with fusion, it's a lot better. Because delta P is not as significant. But in the case of magnesium, it's a big issue because you got a twinning, which deformation mechanism is actually active.
What temperature are you getting to?
Okay, we don't want to go above again. On the pan, magnesium 660, so you like maybe 600.
Okay.
But again, we have developed those for FEM as experiments. So we're dialed in. We know basically what we want. Then we would like to keep it below metal. But if it's too cold, you're left with that cold, cold work. So you don't want to have cold either. You don't want
You
to
still have a thermal zone, won't you?
Yes,
You
this
still
is
have a thermal affected zone.
exactly.
Okay.
This is evidence by good welds that we've made as well as good simulations.
The tool has always been in literature working with this rotating cylinder, and it has this plug. And then you have different properties because the feed rate is different on each side, right? Has any work been done where you have to do some other process than just rotating of the tool, maybe vibrating the tool? Are you aware of that work?
In manufacturing, there's a lot of focus, ultrasound, or vibration.
They do plastic where you vibrate, right?
There's a lot of these applications.
But you get metal, right? They have
And this, I have not really seen this. I did talk about this with Adi at some point. We really never pursued it. It may be good, it may be bad, if you're moving that pin in and out. But it's definitely worth investigating. But I have no idea what the effect would be. I have not seen this anywhere, basically. So yeah, this is